Hello ME400. In this video I'm going to take you through how to solve a Rankine cycle with efficiency. Just a basic Rankine cycle. No reheats or anything. And this question is 8.17 in your I think it's edition 6. So first we start off by writing out our knowns of the problem. So we have pressure 1, 10 megapascals, temperature 1, 480 degrees Celsius, and then we have pressure 2, 6 kilopascals, pressure 3, also at 6 kilopascals, and we also have pressure 4 at pressure 1's pressure, which is 10 megapascals. And then we have the efficiency of the turbine, which is 0.8. The efficiency of the pump, which is 0.7. If at any point if you want to skip ahead to the actual problem, you can. This first slide is just basically saying what our knowns are and drawing the system. So we have a boiler connected to a turbine that moved down into the condenser, which moves into a pump. And that completes the cycle. And these are just the state points that are being that are on the so you know what each one refers to. And then I think I draw the work out of the cycle and the condenser heat leaving and the work of the pump that has to go in. Now we get to move on to the next part, which is actually solving the question. So the first part is to use your tables to find values for state 1. State 1, you are given a pressure and a temperature, which means you have enough to find the values at state 1. The first value is an enthalpy of 3321.4 and an entropy of 6.5284. And for this question, we know we have an efficiency of the turbine, but we have to find the perfect case first. So we assume S1 is equal to S2S. And then we can find our quality, X2S, which is equal to S2S minus SF, and that is the entropy of saturated liquid at 6 kilopascals, divided by SG minus SF, SG being the entropy of saturated vapor at 6 kilopascals. And this part I just write it out. If you want to skip a little bit ahead to see what the actual quality is, you can. And the SF and FG table or values are received from the I think it's table A3 for saturated liquid, or saturated tables for water, which is the working fluid of this cycle. And it turns out X2S is equal to 76, almost 77%. And so, then we move on to solving for H2S. H2S is equal to HF plus X2S times HFG. Since all of these values are known, you can just solve the right-hand side of the equation for H2S. And I think I started to write it out, but then I changed it because I ran out of room. So you don't get to see the values for HFG, or the value for HFG, but you can find that in table A3. Go across to 0.06 bar, and that value is what you will be using for this. And your H2S value ends up being a 2009.88. Now we move on to solving for H3. Well, no, H2 using the efficiency. I got ahead of myself. The efficiency of the turbine. Since we know the efficiency of the turbine, and we know the equation for the efficiency, we can solve for the unknown value, which in this situation is H2. And we have everything in that equation except for H2. So once you maneuver the equation, you should end up getting something like H2 is equal to H1 minus 0.8 times H1 minus H2S. But H2 then ends up being 2272.9 kilojoules per kilogram. Then we move on to solving for H3. H3 is after the condenser. So we know that H3 is always equal to a saturated liquid value, which is HF at pressure 3. So if you go to table A3, you can find the HF value at 6 kilopascals. And this value is 151.53. So for the next part, we move on to solving for the enthalpy after the pump. And so basically what I'm writing here is just that S3 equals S4S. This is just, we are assuming 100% efficiency, just like we did with the turbine, to try and locate an H4S value. And so using the perfect pump equation, which is H4S, that should be an H4S. H4S is equal to H3 plus the specific volume of 3 times the change in pressure from P4 to P3. And this change should be very small. You shouldn't have a massive change from H3 to H4, because if you did, something is wrong. Or your pump is really bad. Either one. And so, since we need V3, we have to go to the tables again, table A3, and find VF to be equal to point, I think it's 0.0010064, I think. Yes. And that's just looking it up in the table value. Just make sure you don't fall for the fact that every value on the VF table is to the negative, or the times 10 to the third. So make sure you get the real one, which is times 10 to the negative third of the value on the table. I just add 2 zeros in front, just makes it easy. And now we solve for H4S, which is the equation we had earlier. I always find that this is the part of the problem that most people go wrong. People just seem to forget the perfect pump equation, and they get stuck here. So just try to remember that right there. Once you have all those written down, you get H4S to be equal to 161.587. And now we have to use the similar tactic we used to find the H2 for the turbine. We have to use the efficiency of the pump for this problem. And since we know the efficiency of the pump is 0.7, we can then solve for our H4 value in the pump equation, since that is the only unknown in the equation. Which is H4S minus H3 divided by H4 minus H3. We put the perfect case on the top because it uses the least amount of work. The perfect pump will use the least amount of work. And you always want to have the efficiency less than 1. And so once you manipulate that equation, you end up getting the following equation: H3 plus H4S minus H3 divided by the efficiency of the pump, which is 0.7. So if you don't have to write that out and manipulate it on every problem. If you can remember the perfect pump one, which is the H4S equation, and the H4 equation, which is very similar to it, just divided by the pump's efficiency, you'll be fine. And it'll be pretty quick instead of having to maneuver the equation to get what you want. And we get an H4 value to be 165. 165.81 or 89. Jump the gun. 897. And so now we can move on to, actually solving what this question is asking. That's always been my philosophy, is to find all the H's and then actually worry about what it's asking. Don't try and solve things before you can. So we are looking for Qn, which is the heat added in the boiler. This is the heat required to get the compressed liquid back to the temperature required at the turbine entrance. So 480 degrees C, because it's already at the pressure that we need, but we need it to be heat added to get there, like temperature-wise, to make work. And so Qn is just the difference in enthalpies of the states after and before the entrance to the boiler. H1 minus H4. Which in this case is 3321.4 minus 165.897. And this gets a Qn value of 3155.5. And we don't have a mass flow rate in this case because it wasn't given and there was no other way to find it. We weren't given a work, or we weren't given a heat in or a heat out of the system. So it's asking us to leave it in kilojoules per kilogram. And now we're solving for the thermal efficiency of the cycle, which is the work net of the cycle divided by the Qn, which is what we just found. The work net of the cycle is just the work of the turbine minus the work of the pump divided by the heat we had to add in. So what you want over what you had to put in for it, which in this case is H1 minus H2 minus the quantity of H4 minus H3 divided by our 3155.5 kilojoules per kilogram. And like I said, if you want to skip a little bit ahead, you can. And I think I end up writing this all out. So if you want to, get to the good part and figure out what the answer is, fine by me. Just make sure you remember where these equations come from and what needs to go where. And as these problems get more complicated, you always want to try and make sure you keep track of what, especially for the thermal efficiency part, what is actually taking place. That's why I said it was important to have knowledge of these cycles. It's because if you don't know what the cycle looks like, where everything's running at, number one, it's going to be hard to solve the problem. And number two, when it comes to the thermal efficiency, you might forget a pump or that's requiring some work, and your thermal efficiency value will be off. So always be aware of what the cycle actually has going for it. And these thermal efficiency values are typically in the 30 to 40% range. So if you get a value that's 90% efficient, I can assure you that you probably done something wrong. And if you are 100% sure that you did nothing wrong, then you need to contact Ameren or some company because you've just discovered the best cycle in the world. And now we move on to part C. Part C is asking for the heat leaving in the condenser. This is the heat removed required to turn our our saturated region water coming out of the turbine into all liquid, so we can pump this up to the final state. And this is usually coming from some sort of heat exchanger, which is a condenser. And so we removed the following: H2 minus H3, and that is equal to the heat removed from the steam to get it to all liquid. And so our Q out for this question is equal to 2120.66 kilojoules per kilogram. I hope you learned something, and thank you for your time.